Hello everybody, welcome to the second lecture, and today we are going to look at logic gates. So as explained earlier, that digital computer systems works on the binary number system using binary signals. So to understand more about the hardware components, you first have to understand about how these binary number system operates, how it works. So, in order to manipulate this binary information, because at the end of the day, it is always processing. What the computer does is the processing and manipulation of binary information. That is what is done by the CPU. So, or even by the other devices. So we have to know how these, what are the operations that can be performed on binary number system, how they can be used to produce the various instructions and operations that we perform in a computer system. And to do that, we have to first understand the operators of the binary number system and the building blocks of the hardware, computer hardware. So the gates, the logic gates, these are, you can call them the building blocks of the hardware. Okay, so the logic gates are some units. You can think of it as a hardware block which takes as input some binary signal. Okay, but when I'm saying binary signal, please remember that it is actually what is and going in is an electrical signal with different volts, and the output that comes out from the logical gate will also be a binary signal or electronic signal, and electrical signal. Now the working of the gates will depend upon the various operations that are there. So, in order to perform the manipulation of this binary informations, we have these logic gates. So, they are nothing but logical circuits which build up the hardware. And there are three things using which we can represent these logic gates. First is you have a graphical symbol. So, there is a notation which we will use to represent the different logic gates. Then each logic gate is represented by an algebraic expression. So this algebraic expression, it will explain what actually is the operation that we are performing. And also finally we have, in a tabular format, we have the inputs to the gate and what is the output. So if input is A, what would be the output? So this is represented in the form of a table which is known as the truth table. So without any more delay, let us start off with the different operations. So let us start with the first one, which is the AND operation. So the operation is AND. This is the name of the operation, and the graphical symbol that is used for the AND operation is something like this. It takes two inputs here. So if I say this is input is A, this input is B, okay, and it gives out one output. Let's say the output is X. Alright, so this is the graphical symbol for AND. Now what does AND do? AND, the output of here X would be 1 only if both A and B are 1. If any of A or B is not 1, that is 0, then the output would be 0. So AND means both A and B must be 1. So you can think of it like this. So both A and B are 1. Okay, so this is the graphical symbol, and the algebraic expression, it is represented like this, that is X, which is the output, is equal to A dot B. So this is dot represents the AND operation. And what is the truth table? So I have two inputs here. This side we write the inputs and this side we write the output. So all possible options. So first, since A and B are binary variables, all of these actually, A, B and X, all three are binary variables. So they can take values 0 or 1. So A can take value 0 or A can take value 1. Similarly, B can take value 0 or B can take value 1. So let us write down all possible options. First is 0, 0. A is 0, B is 0. Then there is 0, 1. Okay. So B is 1 and A is 0. Then this is 1, 0. Okay. A is 1, B is 0. And the final is 1, 1. So as I have described this operation, AND operation, so the AND operation, the output would be 1 only if both A and B are 1. So here I can see I have only this. This is where both A and B are 1. So this is where I will have output is 1. And all other, the output is 0. So this is the truth table. So you can see here I have the truth table. Okay, this is the algebraic expression and this is the symbol, graphical symbol. So this is the AND operator. Next we have the OR operator. I'll go very fast here. OR operator. So the graphical symbol for OR operator is like this. Two inputs. Okay, A and B. Output is X. Okay, it looks like this. And what is the algebraic expression? The operator is represented by plus. This is not addition, remember, this is not addition, but the OR operator. So we write this as A or B. And A or works in this manner. The output would be 1 if any one of A or B is 1. So these are my possible inputs, 0, 1, 0 and 1, 1. So the output would be 1 if any one here is 1. Any one of the input is 1. So here one input is 1. Here also another input is 1. Here both are 1. So my output here would be 0 here because neither A nor B is 1. Here B is 1, so output is 1. Here A is 1, so output is 1. And here both are 1, so output is 1. So this is the truth table for the OR operator. Then we have NOT, also known as inverter. Inverter. So this takes only one input and it gives X. So what it does, if A is 0, it will make it 1, output would be 1. If A is 1, it will make it 0. So the algebraic expression is like this, X equal to A dash. This is also known as complement, A complement, A dash. And the truth table is like this, only one input, so 0 and 1 and X here. So if A is 0, X would be 1. If A is 1, X would be 0. Okay. Then these three, AND, OR and NOT, these are the basic binary operators. Okay. Now there are some other operators which are equally important in construction of digital circuits, but they are not the basic operators. But we will look at these operators also. The next operator is our NAND. N-A-N-D. So our NAND operator, the symbol is like this, graphical symbol is like this, A, B and here X.